Good afternoon, ladies and gentlemen. Today I'm going to talk about my research in maybe next an hour. So the topic of my presentation is about bioinspired structural materials. We're talking about the analysis, the model to analyze them, and how to design them using artificial intelligence, and how to synthesize them with using 3D printing and the technique of how to make it a real product. So I'm Johnny Yu, see it Chi-Hua Yu. I'm from Department of Engineering Science. So my lab is about using artificial intelligence and multi-scale modeling. So let me introduce myself. So I'm Chi-Hua Yu, Chi-Hua. Okay, so also same as Professor Chen. I'm also working with the program on smart and sustainable manufacturing and also Department of Engineering Science. And my research interests mostly focus on artificial intelligence and how to use artificial intelligence to design and understand the mechanism behind some materials. Also, I'm working on multi-scale modeling, so that's why my lab is short for LAIMM, so LAM. Lime is my lab, and so it's focused on two things. One is artificial intelligence, and the other thing is multi-scale modeling. So from early of my academic career, I was working on fracture mechanics. So as you can see here, we design things, materials, and see how they fractures, and to understand the mechanism behind it. And it's also the micro scale mechanism. Also, I'm working on material design, computational mechanics, but recently I've been working on biomaterial designs and also work on biomaterials such as proteins and collagens and some organic compounds that we can analyze and design for pharmaceutical purpose or for some medical usage. Okay, so well, I'd like to thank my team. So this is the whole group of my team with more than 10 more than 10 grad students and more than 7 or 8 undergrad students. I don't know the real number, the exact number. And I have 2 PhD students in my lab, and thanks for their contribution to the work. So I will talk about what we do. Okay, so starting, I'd like to ask a question to all of you. How do we build this amazing world? As you can see here is this National Chinkong University. The landscape, you can see that from the bird view of all the bird's view of what we live here and what we study here. It's a great city. It's a great campus, right? So this wonderful school, how do we build them? How do we build it? And so it's built from concrete or some materials, the steels like that. So let me give you an example. If we like to make it more sustainable, then or like carbon neutralized, we need to make it more high formable and high strength, high toughness, multifunctional. So as you can see, the conventional materials here, to what we have now, we should make it like an order improvement to make a sustainable, eco-friendly, or maybe for the next generation. So that's what we need, and that's how we should do. So as you can see here in metals, the steels and all the structures, they are made by steels. Once we button up from the top down, so you can see the whole structures and some part of it, and then you can see the materials, how to design the materials. So let me give you a way, let me give you maybe philosophy to view this material is a multi-scale modeling. So we can do it from macro scale. So if you take a look at from the this is Eiffel Tower, you can see the tower from kilometers and maybe several meters, dozen meters and 2 meters, and you can see that to a material we can just top down, from a top to the very like nanoscale. You can see here we can have a nanoscale as a fracture pattern, fracture bit. We can have a K field here. You can use finite element to evaluate the process, and we can have a molecular simulations, MD simulations, or maybe the cross-grain simulations to several fibril, and then you can see the atoms. So we can do things in different scale. We can understand the matters and how they interact with each other in this different scale. So that's what we thought. So the problem is, how should we design the next generation of material composite fibers? So the way we can do, we can learn from nature. So from nature, they will have billion years of evolution. So we can so-called the biomaterial, like anchors. They have very similar composite, maybe similar compositions with the calcium coside, but now you can see it's very tough with only 0.5% of the proteins, the anchor proteins. So the secret behind it is what we can learn. So we call it Bioinspired algorithm driven design to discover new materials like multi-scale modeling or genetic algorithm. And then we can do, what we can do is we can use a new tool we have now. So let me show you how we do it. So it's a multi-scale modeling. We have several different ways to do multi-scale modelings, but overall you can see it. We can start from first principle DFT, and then we can have the atoms with a different bond, and to all the atoms, and to the full atom simulations, and to a finite element simulations. So you can see there are different scale, different time scale, different length scale in here. And also, if you take a look at different of the materials we have, or from macro scale, we can have human bones. So if you take look deeper, you can see that from that is a collagen and hydroxyapatite, and also a diatom or the deep sea sponge. What you can see here, we have silica and silicatin. So several different proteins and almost SiO2 silica, sorry, and anchor. Also, we can have aragonite and some proteins. Okay, so cement paste have the same thing. So if we can do the same design on the concrete or reinforcement concrete, that we might be able to change the way and change the world. Okay, so that's start from a very simple way. So if we take a look at the anchor, so anchor is a very specific structure material. So let me show you how this could be impossible to do. Let's think about just a very easy way. It's a tessellated material with a grid structure design. So we have M times M design. So let's think about like nature's. We have two materials from previous, like this one. We have hydroxyapatite and collagens. One is for tough, one is for a strong material, the other one is for compliance soft material. Just have a binary distribution of them. So you can have an M times M design space for toughness and strength optimizations, right? So there will be a layer 6, like an M is the material. So for here is the 2, if we have binary distribution for soft and soft materials and brittle materials, we can have 2 times 2 with the order of n squared. So when we increase the resolutions, as you can see here, there will be intractable numbers. So the brute force of finite element searching, like a commercial way you can do it, is not always feasible. Oh, let me show you. It's almost impossible in finite element that if you have element number increases like this. So the big O is incredibly here. So if you have parallel, it's impossible. Always impossible to find brute force, to find the optimum or global optimizations of your results. So let's see, if we have here, here's what anchor amino acids, and so from the computational aspect, we may need a new way to do regression and design. So the experiment we may use is AI as a new tool here. So let me show you. The first thing to do is using AI to predict complex stress and strain field using deep learning. Okay, so if we can do that, so from previously the design is intractable number, but we have the geometry as a graph or input, so we can have multiple machine learning models or multiple simulation models to evaluate the mechanical properties. But in here we have one machine learning model to do it, and then we can predict not only the, if we can do not predict only the displacement or the stress field, that would be great, right? So how we can do it? We use a GAN approach. The GAN model is like playing a game. So using the game theory, so we have two neural networks working together, deep learning neural to working together. One is dealing with synthesize, that generate some fake images, and the other one is to try to distinguish which one is from the real, which one is synthetic material, synthetic images. And so for this one, there will be a binary discriminator to distinguish them from real and fake, and this one try to create or generate some real images, but it's a fake images. Okay, so it's more like a smart thief or a very experienced agent. The police need to find out which money is fake, which money is real. Okay, so there are two things that maybe make your training miserable. The first thing is the discriminator gets too powerful, like here, why so serious, right? So the discriminator won't be able to tell which one is true or which one is false at the first beginning, so you just fail. And the other one is the discriminator gets too stronger, so this one will make it like you're facing a bad man, so you won't be able to find out which one is which. So this one is generator get too smart, and this one is discriminator get too powerful. And so here we use a pix-to-pix scan, but we make it different modification. So we have here is a generated model. So this generated model is use a UNet as a low-level common features, so they can learn the features from the patterns and some details of that. And then we can show you the way we do with the decoder and encoder. That's why we call it UNet. I will not go through all the details from here, but let me show you. So we have automatic segmentations. You can use UNet to, we can use it for cell or blood vessel. And also the GAN model with a discriminator. Here we use a patch GAN model. So use the patch GAN model to do discriminate as a discriminator. They can tell or distinguish those fake images from the ground truth or not. So let me show you the data populations. This is what we have here, and the black one is for the soft material, and the pink one is for brittle material. We have two different things. One is very brittle, and the other one with ductilities that can withstand longer. Okay, so we have two materials, and then we do data labeling. So we do a compression. So here is a compression. Okay, as you can see, and then we relax it. So we see there's a residual stress and residual strain here. There will be no stress, but there will be at least a residual strain here, as you can see. So the goal of our model is to predict this stress field. We call it residual stress or residual strain. Okay, so the pair input is we give you a composite, and we like you to predict the missing stress contour output and the displacement field. So this is the training flow of a model. We have a training label data and then put them into our game model, we like them. Maybe they can predict the stress field or the strength field. That's the first way we can do is to analyze the composite, the Bioinspired composite. So here's the result. Let me show you. This is the input images. This is the ground truth, the residual stress after compression, and this is the predict outcome. So the game model predict this one, and this is ground truth. So as you can see here, not only the stress field look identical, exactly the same with the ground truth. Also, there shows you, there we show you is the displacement field. As you can see, the age, the prediction of this, we can see that the displacement is also the same. So in this model, we can not only predict the stress, but with several different tensor components, not just MISI, we can also show you the different components from there. So that's what we have, the accuracy. We show you the accuracy from our predict contour is way better than other methods with some random guess. So also you can find some derived property from our model. So the derived property maybe maybe from MISI stress you can do with the residual stress average. So we can just make a, maybe we call it a recoverability. So average residual stress, we call it recoverabilities. So the lower the value, which means the more the strain energy being released and stored. Okay, so the top for recoverability from finite element, which means the simulation method we use for commercial software, and the top for recoverability from machine learning, they show exactly the same thing. So here we have not only the stress field, but also the derived field. So can we do more? Yes, in this model we can do a hierarchical pattern district design. So we use the low resolution in our design space, but they can do with a high resolution, like a super resolution prediction. But as you can see here, it's something that we still have something that you can work on. So for the super resolution or high resolution, we need maybe some new algorithm to do so. But for the machine learning model here, so we can also predict not just the square pattern. So we can see the regular grid, it's okay, but the different geometries, we haven't put them into the model. But here we can show you here the different geometry. They can show you the same ability to predict. So we can use it to predict honeycomb or diamond structures. So as you hear, also we can show you, we can do is the multiple loading conditions, different loading conditions at the same time. So we can apply the compression also with the indentation here, so you can make a combination with them. So the stress, the ground truth, and the prediction shows you a wonderful result here. So you can see that we can do a combination by both of them. And also the super resolution I show you. So you can see we use the same, the low resolution predict the pre-trained model to predict this geometry. This is MIT dome from building 5, building 10, not building 5, building 10. So you can see it. It's wonderful, right? And so the result here. So here we can predict different contour, different geometry, and different resolutions, different field. We can do stress, strain field. So, but can we do more? The problem I showed you before is the super resolution or high resolution. Because of what we want to do is increase the design space. And can we do that? So we show you a new way is to design tough and strong bonds by a composite use reinforcement learning. So when we talk about reinforcement learning, I have to show you that is AlphaGo. So AlphaGo is a software developed by Google's company they call DeepMind. So DeepMind just announced it in 2016, and all over there the AI went viral everywhere. People are talking about reinforcement learning, talking about machine learning. So after that, big data is not, I think it's not big enough. We are pursuing huge data, mega data from them. So from till today, 2020, 22, people are always talking about how many data do we need, and let me show you the good thing of using reinforcement learning. So this is resolution with 32 times 32. I think a way higher than what we show you 8 times 8 before, right? So if we like to do that, can we do an automatic design using reinforcement learning? So if you take a look at this design space, it's pretty much similar to a goal, the ball of gold, the chase ball, right? So we can use the same strategy to do so. So the reinforcement learning here, we also like to design a tough and strong material. So here is a pre-crack, the initial crack. If we have a composite and with the initial crack, can we make it more tough or make it either stronger or tougher? So here we have the algorithm called reinforcement learning algorithms we have here is there will be an environment. So sorry, we need an environment here. So the environment will put your material into an agent, and agent will do some exchange or sweep from they may changing soft material and brittle material. They can switch or they can change something. So the environment will have to evaluate the rewards. Is it getting better? Or if not, they will give you a negative reward or zero reward. And if it gets better, it will show you there's a positive reward or maybe give you 1 like this. So after several iterations, you will have acceptable or maybe optimum design. So let me introduce you to Q-learning. So the Q-learning is the simplest way to do reinforcement learning. So let me show you. Here we have an initial map state, and with a material map, we can do exchanging. The exchanging is called a Q table. The Q table would record all the states, and then we can do some changing, and the environment will show you the rewards, and we can update the Q table to the first thing. So they will call an iteration. So after that, finally, we'll give you maybe the convergence of the result, and we can say that we have an acceptable design here. So here's the data labeling. We introduced from previous experience, we introduced more challenging problem. So we introduce an initial crack here, and then you can see that we apply a different displacement control with the different Young's modules. This is artificial materials, but we can introduce some new real material instead. We'll show you the result later, but let me so today here we introduce a new way to do reinforcement learning. It's called hierarchical design paradigm. So we can design starting from a very low resolution design space and make it to a higher resolutions with a higher design space. We call from 8 times 8 to 6 times 6 to 32 times 32. And as you can see here, we have the design space, the best design of all of them. You can see the distribution or resolution are different. Also, you can see the stress concentrations at the crack tip. We have the dramatically decrease. Okay, the stress concentration here is high, but for now, we only exist here. Okay, so maybe you have a question there. So the stress concentration is still high, but let me remind you, from here the material is perfect, intact, so there will be no problem to withstand this amount of material, this amount of stress. But if you put this stress concentration at the crack tip, this material won't be able to withstand this high volume of the stress or the force, right? So that's why let me show you here. So with the different resolutions, we can see which one is more important to the design. So as you can see here, we have the optimum design from 32 times 32 here. As you can see, we remove the bottom one. So as you can see, if we remove the bottom one, the stress concentration will be introduced back, because there is no stress guidance here. So they're just like a guideline. They will guide the stress back to a different place, as you can see here. And also we can switch the bottom, the top. We can remove the top, as you can see here. The stress concentration increase higher. But if you remove the bottom one, there will be, you know, the stress concentration was severely just trapped into it, before or located in front of the crack tip. So it will make this material cracking faster and dramatically. Also, we have a 3D printing result and show you the DIC with the strength field. This is what we design here from A times A, and 6 times 6. You can see the result shows a great agreement from the experiments and our design. So you may say that you can only apply to polymer, right? So not just a polymer, also apply to hydrogel. Not just printed polymer, I can use it for self-healing hydrogel or some brittle materials that you like to use with hydrogel. So that's why we have it. Let me show you the videos of the hydrogel with the printed pattern that show excellent ability to withstand this crack. So usually they were just already cracked, but as you can see now, this crack has no longer propagated. Instead of the material at the edge just exists its ability to withstand this stress, so it reaches the nature optimal stress. So in here we may push the stress concentration higher, but we remain the integrity of the materials by this reinforcement learning design. Okay, so as you can see here, we can have this 6 times 6 also shows you the same thing. The higher the stress concentrations will be propagated to this. So the materials, if you do just the perfect material, they will also break from somewhere here. So it's here. As also you can see here, we have the highest resolution. We have the 32 times 32. The result, as you can see here, as I show you the videos, we can withstand longer and longer. And the material break not from the crack tip, but from some place else. Okay, so that's what we expect. The material will no longer propagate at the crack tip, but from the perfect material. So which means it will exist exact or maybe higher than what we have now. Just the applying stress just above the material's limit or the ultimate stress. So which means it's the way we can do is to remain the integrity of the material and push the stress concentrations to the perfect material. Okay, so let me show you the way we do from the polymer that show you the tension from the tensile stress with the hydrogel materials. Okay, so that's good thing that which shows our material, that the material design shows perfect and ideally. Okay, so the design is working, but the next question, can we synthesize it or can we make it more differently? So yeah, sure. So we are talking about from a composite design to analyze them and how to synthesize. Before we talk about synthesize them, we need to do something first. The first thing is how to generate it. Besides the 3D printing, the one thing we can do is freeze casting. So like to generate those architect material or porous material, you need to be able to control the porosity or the properties and everything that we need. So we do get interest in this one. So the ice solidifications and porosity, that would be one interesting problem to take a look before we like to generate or synthesize materials. So we can do, as you can see, it's a freezing problem, ice solidification problem. So the most common way to solve it is use phase field. So we can given a different material, different initial temperatures, we can control them and to generate new generated, and then we can put them into a machine learning model. Let the model learn how the physics behind those ice get solidifications and the freezing and the porosity, how to determine it. So there will be two different ways from the supercooling. We have the single plate and needles, the morphology like the needles and the dendritic structures. This is the most one we want, but we can control it. So we also use a deep generative model. So this model is a new model to do so. So in our case, we can show you that if we have an input case, we can predict the results from this is the beginning and the output. So we can show you that the predictions of our model is great, and we show you that the SSIM is identical, which means it's a good agreement with that. And then we can show you the ground truth and our output model. So this is our models. We can show you that the prediction is perfect. And also we can predict different morphologies. We can show different porosity, different morphologies from our model. And you can generate sequentially to see how this model can vary with time. So from previous, we can predict a certain time with morphology, but also we can do with the generation of the iterations of how this ice morphologies will evaluations of them and evolution of them, and how they grows across in the domain, and how to see that. So as you can see here, we can predict the supercooling rate, and by controlling the supercooling rate, we can with a different morphologies, right? This is dendritic, and this one is for the needle. So if you compare with the experiments, we can show you that with a different supercooling rates, you have a dendritic from to the plate and to this single plate model. Okay, so by controlling the supercooling rate, a machine learning model can also capture this physics behind the ice solidification. So it's interesting. So we can use it. Could we use it in designing biomaterials or bio-inspired material? Can we do that with extraordinary properties and some intricate structures and microstructures? So from previous, we know how to generate things from time. But if we think about the time is a slice in the space, we can use the same approaches to generate porous material. That's the goal. So we're starting from there. We learn the metamaterials called dry rate structure. So dry rate structure can be found from the wings of butterflies. So the dry rate can be treated as a more strong material if you compare with the relative density. It should be 5 times stronger than steel, and the data statistic, you can use it, use this similar function to generate dry rate structure. So we also have some nature materials like antlers. So if you take a look at antler, you can see that their antler have different snapshots. You can use obtain from a CT scan. So can we do so? Can we learn from the nature structure using the same approach? We predict the ice morphologies to predict the structure continuity. So here we introduce a transformer like what we used before, and then that's the idea of how to training. We'll not go through all the details, but we can show you that is how we can predict and generate slice by slice. So we put some slice into as input, and then we can generate rest of the images. So for instance, if you give them the first 5 slices, they will generate new slices. So this is because we know how the dry rate looks like, so we can predict dry rates to see how this model can predict, and then we can put them into different biomaterials. So This is our original data, and this is the generated output. They look identical and look pretty similar to each other. So we can show you the continuity of our model, shows a great continuity of them. And also, the porosity shows the similar trend of the different axes with the label, which means the ground truth shows you the great ability of how we can learn and the long-term homology of our model. So you can put some random noises to generate different type of gyro structures, as you can see. So the gyro will have a more variations from this model. So after we check the results from gyro, we shift the gear to synthesize the real material, biomaterial. So for example, we use antler as an example. So as you can see, the continuity from random blob and antler, you can have a slice generated antler and vector generated antler. They show you the similar trend. The similarity is pretty similar to the real one. And also the porosity profile here show you the same trends that we can use here. So the result of gyri and the result of antlers, I can put them into together and to compare the result here. So here we have a model to generate 3D structures with high porosity, different morphologies. But can we synthesize them? So this is a shoe from Adidas and Under Armour's and New Balance. It's called 3D printing for the shoes, and they use the ideas from meta structures. But what we started before, what I showed you before is a gyro structure, the wind gyro composite. You can use a gyro lattice to do so. So as you can see here, we have toe, arch, heel. They may need to optimize with different objectives. So for instance, if you like to design the heels, they may have a high energy absorptions and low reaction force, but with high support. So you may have the stress concentration lower, but the resulting force is higher. Okay, for instance, like this one. So at the same thing, we can generate gyri, and then we can combine them with the previous composite design reinforcement learning. So we create a paradigm of framework that we can design a shoe, the midsole of a shoe, with a high energy absorption, lightweight, with acceptable or adequate support. So from here we have stiff materials and soft materials with different type of gyri. So as you can see, this is our design space. And then for heel and for arch and toe, we have different design philosophies. You can use reinforcement learning to do so. So that's starting from a unit cell. We have different gyros and F-type and S-type or strong IWP type structures, and we print them out and do the testing. As you can see here, they respond to the compression differently. So as you can see, gyri with local buckling. And the funny thing is, when we release it, unload all the loadings, they will gradually recover back to the original shape. That's incredible for gyri. So the 3D structure, you can mixing them by gyro with antler or different kind of gyro or different kinds of meta structures. So let me show you that is our machine learning model to predict and to synthesize them. So here what we have, different materials, gyroid, fissure, knocks, and diamonds. You can just put them together and then to mix things or fusions and whatever you want to meet your design goals. So we printed them. It's pretty fascinating, looks amazing. And let me show you more pictures from that. And so From the printed unit cell, we can do is a design building block that we can do to determine the master curve of what we have the module's plateau stress, and put them into a reinforcement learning algorithm. So as you can see here, we have material maps and do the same thing from previous reinforcement learning, and we can use it to design shoes. So we can have heel, the best design for heel, and the best design for arch, and the best design for the toe. So after that, we put them all together. So this is our midsole, the printed midsole. So we also printed out with here is a slipper. So you can try it on and to see how it looks like. So you can see here, this is the real midsole and this is slipper. After the printed product, we put them into a falling mass shock absorption test central TM142 to see the energy absorption rate and pick decelerations. If they they meet the design requirement, and the results shows if they show the same trend of what we designed. So as you can see here, the toe and the heel, we design for reduction for the energy absorption. So you can see that the top acceleration been decreased, and which is good, which means that the heel has the most energy absorption rate, and the toe has average energy absorption rate, which meets the design requirement. So finally, I'll talk about some thoughts that you can take away as if we are moving from virtual processing to virtual generating. The virtual processing is more about how to determine the properties or the mechanisms behind some compounds or substance that you've been maybe synthesized from a lab, or maybe create the forge from some specific metals. But a robust of model manufacturing design using AI, I think it's a unique way. We show you several models in the sequel. That is a unique way to increase the strength of product design. And also, this framework can be easily extended to different systems of biomaterial design, protein design. I have another talk on TMS to talk about that. And instead of using AI, I would suggest all of you try to using AI plus X, where X is your domain knowledge acquiring high quality data. Okay, and I think that's all for today's talk. Thank you so much. And if you have any questions, please feel free to contact me. I'm more than happy to answer your question. Thank you so much.